Somewhere in the constellation Cygnus, 20,000 light-years from where you are lying right now, there is a point in space where the laws of physics, as we currently understand them, simply stop working. Not slow down, not bend, stop. Cease to offer any prediction at all. Every equation that has ever successfully described the universe, the equations that put spacecraft on the surface of Mars, that predicted the existence of the Higgs boson before it was found, that tell us precisely how a star will live and die, every one of them breaks down completely at that point, and none of the smartest people who have ever lived have been able to fix them. We call that point a black hole, and here is the thing that should stop you if you sit with it for a moment. It is not a hole in the conventional sense. There is no gap, no emptiness, no absence of anything. It is, in fact, the densest, most extreme concentration of something the universe is capable of producing. A black hole is not a void. It is too much of everything compressed into too little space until space itself gives way. Think about what that actually means. Take an object with the mass of our Sun, 1.99 times 10 to the 30th kilograms, more mass than every planet in our solar system combined many thousands of times over, and compress it. Not by half, not by a factor of 10. Compress it down until it is smaller than the width of a small town, 6 kilometers across. That is what it would take to turn our Sun, exactly as it is, into a black hole. Every atom crushed into a sphere you could walk across in an afternoon. Our Sun will never actually do this. We will get to why shortly. But somewhere out there, other stars have. And when they did, they created something that does not merely resist our understanding. It actively erases the tools we use to understand anything. Here is the specific problem, stated as plainly as I can state it. Inside a black hole, at its very center, general relativity, Einstein's theory of gravity, the most successful and thoroughly tested theory of gravity ever devised, predicts something called a singularity, a point of infinite density, infinite curvature of space-time, a point where the mathematics does not describe extreme physics anymore. It describes nothing at all. The equations simply stop returning an answer. Physicists have a name for what this means, and it is an uncomfortable one. It means that inside every black hole in the universe, there is a place where our best theory of gravity admits, honestly and without qualification, that it does not know what is happening. We are going to spend tonight with that place. Not to solve it. No one has solved it. Not yet. Possibly not for a very long time. But to understand exactly how we know black holes are real, what happens as you approach one, what we now believe waits at the edge of one, and why the deepest mystery in physics is not actually the black hole itself. It is the boundary around it, the point of no return, and what that boundary does to information, time, and the very idea of a past and a future. Let's begin with the man who calculated it should exist, sitting in the middle of the First World War, working from a battlefield where he had almost no reason to expect he would live long enough to see if he was right. In December 1915, Albert Einstein published the field equations of general relativity, 10 interlocking equations describing how mass and energy curve the fabric of space and time, and how that curvature, in turn, determines how matter moves. They are, by near universal agreement among physicists, among the most beautiful and most difficult equations in the history of science. Einstein himself did not expect anyone to find an exact solution to them for years, if ever. The equations were simply too complex, too interconnected, too resistant to the kind of clean mathematical treatment that produces a precise answer. Within a month, someone had found one. His name was Karl Schwarzschild. He was a German physicist and astronomer, already accomplished, already respected, and at the time he made his discovery, serving as an artillery officer on the Eastern Front, calculating trajectories for the German army during some of the bloodiest fighting of the First World War. He had volunteered for military service despite being over 40 years old, well beyond the age of conscription. He worked on his physics between duties, in whatever hours the war allowed him. In late 1915, word reached the front of Einstein's newly published equations. Schwarzschild, working from memory and whatever mathematical resources he could access in the field, found an exact solution describing the space-time around a perfectly spherical, non-rotating mass. He wrote up his findings and sent them, by mail, from the trenches to Einstein in Berlin. Einstein was reportedly astonished. He presented Schwarzschild's solution to the Prussian Academy of Sciences himself on Schwarzschild's behalf in January 1916. Schwarzschild's solution contained something strange embedded within it. The mathematics described a specific radius, a distance from the center of the mass, at which the equations began to behave in an extraordinary way. Inside that radius, the roles of space and time, in a sense, reverse. Falling inward becomes as unavoidable as the forward passage of time is for us. And at the very center, the equations produced that troubling result we mentioned a moment ago, a singularity, a point of infinite density where the mathematics simply stopped making sense. This special distance came to be called the Schwarzschild radius. For any given mass, there is a specific Schwarzschild radius, the size that mass would need to be compressed to in order to become what we now call a black hole. For the Sun, as I mentioned, that radius is about 3 kilometers. For the Earth, it is smaller still, about 9 millimeters. If you compressed the entire mass of the Earth down to the size of a marble, it would become a black hole. For decades after Schwarzschild's discovery, most physicists, including Einstein himself, assumed this was a mathematical curiosity rather than a description of anything that could actually exist in nature. Surely, they reasoned, no real physical process could compress matter to that extreme. The singularity at the center was treated as evidence that something must be wrong with the solution, or with the assumption that it applied to real objects rather than evidence that black holes were physically real. Schwarzschild did not live to see this debate unfold. He developed a rare autoimmune skin disease while still serving on the front and died in May 1916, just months after his solution was published. He was 42 years old. It would take nearly half a century, and the death throes of massive stars, for physicists to accept that what Schwarzschild had found in the trenches was not a mathematical oddity. It was a description of something the universe makes, routinely, whenever a sufficiently massive star runs out of fuel. For most of a massive star's life, it exists in a state of magnificent continuous balance. At its core, nuclear fusion converts hydrogen into helium and later heavier elements, releasing an extraordinary quantity of energy in the process. That energy pushes outward, generating pressure that resists the star's own gravity, which is constantly trying to pull the star's mass inward and collapse it. For as long as the star has fuel to burn, these two forces, outward pressure from fusion, inward pull from gravity, remain in equilibrium. The star holds its shape, sometimes for millions of years, sometimes for billions. This equilibrium cannot last forever. Eventually, the star exhausts the fuel available at its core. Fusion slows and then stops. The outward pressure that had been holding gravity at bay for the star's entire life disappears. Gravity, unopposed, wins. What happens next depends entirely on how much mass the star has. For stars roughly the mass of our Sun or somewhat larger, the core collapses until a new kind of pressure, one arising from quantum mechanical rules about how tightly electrons can be packed together, halts the collapse. The result is a white dwarf, an extraordinarily dense object, roughly the size of Earth, containing roughly the mass of the Sun. Our own Sun will end its life this way, in about 5 billion years. It will never become a black hole. It does not have enough mass. For stars considerably more massive, roughly 8 to 20 times the mass of the Sun, the collapse is more violent. The core collapses so completely that even electrons are forced to combine with protons, producing neutrons and releasing a burst of subatomic particles called neutrinos, so immense that it can, briefly, outshine the light of every other star in the galaxy combined. This is a supernova, one of the most energetic events the universe produces. What remains at the center, if the collapsing core's mass falls within the right range, is a neutron star, an object with roughly 1.5 times the mass of the Sun compressed into a sphere about 20 kilometers across. A neutron star is so dense that a single teaspoon of its material would weigh, on Earth, about the same as a mountain. But for stars more massive still, generally more than 20 times the mass of the Sun, even the extraordinary pressure that supports a neutron star is not enough. There is no known force in physics capable of halting the collapse. The core continues to compress. It passes through the point where it would have stabilized as a neutron star and keeps going. There is nothing left to stop it. It collapses to the Schwarzschild radius, and beyond. A black hole is born. This is not a rare or exotic event on the scale of the universe. Massive stars, though less common than smaller stars like our Sun, exist by the billions across the Milky Way alone, and stellar mass black holes are thought to number in the tens of millions within our galaxy. They are, cosmically speaking, an unremarkable byproduct of how massive stars end their lives. Nature has been manufacturing them for as long as massive stars have existed and died, which is to say for most of the history of the universe. The theoretical case for their existence, established through decades of careful astrophysics, is not the difficult part of this story. The difficult part is what a black hole actually is, once it exists, and how we ever manage to confirm, observationally, that these objects are real. For decades after black holes were theoretically predicted, they remained precisely that, predictions. No one had observed one. Given that a black hole, by definition, emits no light of its own, the very idea of directly seeing one seemed almost paradoxical. How do you find something whose entire defining characteristic is that it cannot be seen? The answer, it turned out, was to look not at the black hole itself, but at its effect on something nearby. In Cygnus, one of the brightest and most easily observed constellations visible from Earth, astronomers had long studied a bright, ordinary-looking star catalogued as HDE 226868. In 1964, an early X-ray observation satellite detected an unusually powerful source of X-rays coming from that same region of sky. The X-ray source was named Cygnus X1, the first X-ray source catalogued in the constellation Cygnus. X-rays are not something ordinary stars produce in large quantities. Their presence at this intensity demanded an explanation. Through the late 1960s and into the 1970s, astronomers gradually pieced together what was happening. HDE 226868 was not alone. It was orbiting something massive, something invisible, something that was pulling gas from the star's outer atmosphere and dragging it into a spiral where the gas compressed, heated to millions of degrees, and radiated the X-rays that had first drawn attention to the system. The mass of the invisible companion could be calculated using the same orbital mechanics that let astronomers weigh planets and stars throughout the universe. By observing how the visible star wobbled under its companion's gravitational pull and how quickly it completed each orbit, the calculation produced a mass of somewhere between 15 and 21 times the mass of our Sun, confined to a region of space no larger than a small planet. There was no known type of star, no neutron star, no conceivable ordinary object that could account for that combination. That much mass, confined to that little space, remaining completely invisible except for the X-rays produced by material falling toward it. It had to be a black hole. The case was strong enough that in 1974, physicist Stephen Hawking made a famous wager with his colleague Kip Thorne, betting that Cygnus X1 was not, in fact, a black hole. A bet Hawking later said he made partly as a form of insurance, so that if black holes turned out not to be real after all, he would at least have the consolation of winning the bet. In 1990, having become convinced by the accumulated weight of evidence, Hawking conceded. He broke into Thorne's office while Thorne was away and signed the concession himself. Cygnus X1 is now recognized as one of the best established stellar mass black holes in the galaxy and remains an object of active study. In August 2026, astronomers using a combination of radio and X-ray observations announced they had, for the first time, precisely measured the power and structure of the relativistic jets being launched from Cygnus X1. Narrow, extraordinarily energetic streams of particles blasted outward from the region surrounding the black hole at velocities approaching the speed of light, carrying power roughly equivalent to the total output of 10,000 suns. Those jets are not coming from inside the black hole itself. Nothing escapes from there, but from the extreme environment immediately outside it, where infalling matter is accelerated to tremendous speed before some of it is flung back outward rather than falling in. The star that first drew astronomers' attention in 1964 is still there, still visible, still orbiting something none of us will ever see directly. Its light is the only reason we know its invisible partner exists at all. For more than a century, ever since Schwarzschild found his solution in the trenches, black holes remained something humanity could only infer. We measured their gravitational effects. We detected the radiation from matter falling into them. We calculated their masses from the orbits of objects nearby. But no one had ever produced anything resembling a direct image. This was not merely a matter of technological limitation, though the technology required was formidable. It was a matter of scale. Even the nearest supermassive black hole to Earth, the one at the center of our own galaxy, called Sagittarius A star, is so distant and its event horizon so comparatively small despite containing roughly 4 million times the mass of our Sun, that photographing it from Earth would be, by one commonly used comparison, akin to photographing an object the size of an orange located on the surface of the Moon. No single telescope on Earth has a mirror large enough to resolve something that small at that distance. The physics of optical resolution simply does not allow it. The solution that astronomers eventually developed was ingenious. Rather than building one impossibly large telescope, they linked together radio telescopes at observatories scattered across the entire planet, from Antarctica to Hawaii to Spain to Chile, and combined their data using a technique called very long baseline interferometry. In effect, they turned the entire Earth into a single telescope with an effective diameter as large as the planet itself. The project was named the Event Horizon Telescope. It began coordinated observations in 2017, focusing first not on our own galaxy's black hole, but on an even more massive target. The supermassive black hole at the center of a galaxy called M87, located about 55 million light-years from Earth, with a mass estimated at 6.5 billion times that of our Sun. The observation itself required extraordinary coordination. Multiple telescopes on different continents, in different weather conditions, all needing clear skies simultaneously, all recording data with atomic clock precision so that the signals could later be combined. The resulting data was so voluminous that it could not be transmitted over the internet. It had to be physically flown on hard drives to processing centers for analysis. On April 10, 2019, the Event Horizon Telescope collaboration released the result, the first direct image ever produced of a black hole's shadow, a glowing asymmetric ring of superheated material orbiting a dark central void, the shadow of the event horizon itself, silhouetted against the light of the material falling toward it. It was not a photograph in the ordinary sense. It was constructed through immense computational effort, and the image itself represented weeks of observation compressed into a single averaged view. But it was, unmistakably, a direct visual confirmation of something that had existed until that moment only as mathematics and inference. The ring, its shape, its size, matched with extraordinary precision what Einstein's century-old equations had predicted a black hole's shadow should look like. In 2022, the same collaboration released a second image, Sagittarius A star, the black hole at the center of our own galaxy. Smaller, closer, but far more difficult to image precisely because matter orbits it much faster, completing an orbit in minutes rather than days, meaning the black hole's appearance changes noticeably even during a single night of observation, blurring the image the way a long-exposure photograph blurs a moving subject. The team overcame this by developing entirely new imaging techniques capable of accounting for that rapid variability. Two black holes, photographed in the only sense that word can meaningfully apply to something that emits no light, both matching Einstein's predictions to a degree of precision that left even seasoned physicists visibly moved. We had not merely confirmed black holes exist, we had, for the first time, seen the edge of one. Let's be precise about what that image actually shows, because the event horizon is one of the most commonly misunderstood concepts in all of astrophysics. The event horizon is not a physical surface. It is not a wall, not a membrane, not a boundary made of any kind of matter. It is a mathematical threshold, a specific distance from the center of a black hole, corresponding exactly to the Schwarzschild radius at which the escape velocity required to leave that region exceeds the speed of light. Escape velocity is a familiar concept. It is the speed an object would need to travel to break free from a gravitational field entirely, rather than falling back down. Earth's escape velocity is about 11 kilometers per second, which is why rockets need to reach that speed to leave orbit permanently. The more massive and compact an object, the higher its escape velocity. At the event horizon of a black hole, the escape velocity equals the speed of light, the fastest speed anything in the universe can travel, according to everything we currently understand about physics. Cross that threshold, moving inward, and no signal, no particle, no form of information of any kind can ever travel fast enough to escape back out. Not because of some barrier stopping it, simply because the geometry of space itself, at that point, curves so extremely that every possible direction of travel leads further inward. Think about it this way. Under ordinary circumstances, you can choose your direction of travel through space, while time moves forward regardless of what you do. Inside the event horizon, this relationship inverts. Falling toward the singularity becomes as unavoidable, as inescapable, as the forward passage of time is for you right now, lying in bed. You cannot choose not to move toward tomorrow. Inside the event horizon, matter cannot choose not to move toward the center. This is why nothing, not light, not matter, not information of any kind, can climb back out. Once it has crossed that boundary, it is not a matter of insufficient engine power or clever maneuvering. Every possible path forward inside that boundary points inward. What would it actually be like to fall toward one? For a sufficiently massive black hole, a supermassive one like Sagittarius A star, the answer is disconcertingly almost nothing at all. Because the black hole is so large, the difference in gravitational pull between your head and your feet as you crossed the event horizon would be negligible. You would notice no dramatic sensation. You would cross the point of no return without any local signal that anything had changed. For a smaller, stellar mass black hole, the experience would be entirely different and considerably less gentle. The gravitational gradient across a small black hole is so extreme that an object falling toward it would experience wildly different gravitational forces between its near and far sides, a process astrophysicists have, with a certain dark wit, named spaghettification. The tidal forces would stretch any falling object into an increasingly long, increasingly thin filament, well before it ever reached the event horizon. Either way, gently or violently, the outcome beyond the horizon is the same, and from the perspective of anyone watching from a safe distance, something else entirely strange happens. Due to the way gravity warps time itself near a black hole, an object falling toward the event horizon appears, to an outside observer, to slow down as it approaches, its light growing dimmer and more red-shifted, seeming to freeze at the horizon rather than visibly crossing it, even though from the falling object's own perspective, it crosses the boundary in finite time, without any sense of having paused at all. Two completely different experiences of the same event, depending entirely on where you are standing. That divergence is not a curiosity. It is a direct consequence of one of the deepest and strangest features of Einstein's physics, that time itself is not universal. It bends differently for different observers depending on their position in a gravitational field. And it is only the beginning of the strangeness, because once you ask what happens to information that falls across that boundary, physics runs directly into one of its most serious unresolved problems. In 1974, Stephen Hawking made a discovery that complicated the picture of black holes considerably, and in doing so, opened one of the most contentious debates in modern theoretical physics. Applying quantum mechanics to the region immediately outside a black hole's event horizon, Hawking found that black holes are not in fact perfectly black. They should, over immense timescales, emit a faint stream of radiation, now called Hawking radiation, arising from quantum effects at the boundary of the event horizon. This radiation, Hawking calculated, carries energy away from the black hole, and if a black hole is losing energy, it is losing mass, very, very slowly. For a stellar mass black hole, the process would take vastly longer than the current age of the universe. But the implication was profound. Black holes are not eternal. Given enough time, they evaporate. This raised an immediate and deeply troubling question. If a black hole eventually evaporates completely, disappearing into a final burst of radiation, what happens to all the information that fell into it over its lifetime? Every particle, every photon, every physical detail about every object that has ever crossed its event horizon. Does that information simply vanish from the universe when the black hole finally evaporates? This would violate one of the most fundamental principles in all of physics, that information cannot be destroyed. Not lost, not hidden, genuinely, permanently destroyed. Quantum mechanics, one of the two great pillars of modern physics, insists that the information describing a physical system's state must, in principle, always be recoverable, even if doing so is practically impossible. If Hawking radiation carries no trace of what fell into the black hole, if it emerges as pure, featureless thermal noise, exactly as Hawking's original calculation suggested, then black holes appear to violate this principle. Information would genuinely be lost. This is called the black hole information paradox, and it has occupied some of the finest minds in theoretical physics for half a century. It matters because it represents a direct collision between the two great theoretical frameworks of modern physics: general relativity, which governs gravity and predicts the existence of black holes and their event horizons in the first place, and quantum mechanics, which governs the behavior of particles and insists that information cannot be destroyed. Both theories are extraordinarily well tested within their own domains. Neither has ever failed an experimental test, and at the event horizon of a black hole, they appear to directly contradict one another. The proposed resolutions are numerous, mathematically intricate, and so far unconfirmed by direct observation, which is itself unsurprising, given that testing them would require probing physics at the event horizon of an actual black hole, something no experiment on Earth can currently do. One influential proposal, developed substantially by physicist Leonard Susskind and others, suggests that information is not actually lost, but is instead somehow encoded on the event horizon itself in a way that preserves it and allows it in principle to be recovered in the Hawking radiation, though the mechanism by which this happens remains fiercely debated and only partially understood. A more recent and, in some ways, more radical family of proposals suggests that the resolution requires rethinking whether an event horizon, as classically conceived, is even the correct picture of what surrounds a black hole. Some physicists have proposed the existence of what they call a firewall, an extreme, high-energy boundary at the event horizon that would destroy anything crossing it in a manner entirely different from the gentle, unremarkable crossing predicted by general relativity, resolving the information paradox at the cost of overturning long-held assumptions about what an observer would actually experience falling in. None of these proposals has achieved anything close to consensus. What has emerged over decades of intense theoretical work is a shared conviction among most physicists in the field that Hawking's original calculation, however brilliant, cannot be the final word, that some mechanism, not yet fully understood, must be preserving the information after all. Hawking himself revised his own position over the following decades, eventually proposing before his death in 2018 that information does escape, encoded in subtle correlations within the radiation in ways too complex for any external observer to practically decode, but present nonetheless in principle. The debate continues. It sits unresolved at the exact point where our two best theories of physics refuse to agree with one another, which is, not coincidentally, precisely the same point where the mathematics of a black hole breaks down entirely. Not every black hole is actively devouring nearby matter, glowing with the radiation of infalling gas, or launching jets that outshine galaxies. Most of the time, most black holes are simply quiet. This matters because it complicates one of the most persistent popular misconceptions about black holes, that they behave like cosmic vacuum cleaners, aggressively pulling in everything around them across vast distances. This is not accurate. A black hole's gravitational influence beyond a certain distance is identical to that of any other object of the same mass. If our Sun were somehow replaced with a black hole of precisely the same mass, an alarming thought but a physically instructive one, Earth's orbit would not change at all. We would simply lose our source of light and warmth. The black hole would exert exactly the gravitational pull the Sun currently does, no more. Black holes only consume matter that comes close enough to fall within their gravitational influence, exactly as any massive object would. Most of the time, in the vast emptiness of space, there simply isn't much nearby matter to consume. A black hole that has already cleared its immediate surroundings can sit quietly, essentially invisible for extraordinarily long periods. This makes dormant black holes remarkably difficult to detect. We generally rely on their effects on visible companions, as with Cygnus X1, or on gravitational lensing effects when they happen to pass in front of more distant light sources. Many black holes, quite plausibly, remain entirely undiscovered simply because nothing nearby is currently revealing their presence. Occasionally, though, something changes. A star wanders too close, a gas cloud drifts within reach, and a previously dormant black hole reawakens. In April 2026, astronomers reported observing exactly this kind of event. A supermassive black hole, quiet and undetected for what evidence suggests was roughly 100 million years, suddenly began flaring dramatically in X-ray and ultraviolet light, consistent with a fresh influx of infalling material igniting activity around it for the first time in longer than most species on Earth have existed. Events like this, called tidal disruption events when they involve a star being gravitationally shredded as it passes too close, offer astronomers a rare and valuable opportunity, a chance to study the immediate environment around a black hole's event horizon in real time, watching the physics of infall and radiation unfold on timescales of days and weeks rather than waiting passively for pre-existing activity. These sudden reawakenings are also a humbling reminder of something easy to lose sight of amid the mathematics and the imaging technology. Black holes exist on timescales that dwarf human history entirely. 100 million years of quiet, followed by a flare that astronomers happened to be watching for. The black hole did not know or care that we were watching. It simply responded, as it always would, to a change in its immediate surroundings, continuing a process that has been playing out, largely unobserved, across the galaxy for billions of years. We are latecomers to this story, arriving with instruments sophisticated enough finally to notice. There is something unusual, philosophically, about a scientific theory that predicts its own failure. General relativity does exactly this. Applied to a black hole, Einstein's equations do not merely describe something extreme. They describe a point, the singularity at the very center, where the theory itself stops producing meaningful answers. Infinite density, infinite curvature, not a very large number, an answer that is not a number at all in any physically sensible sense. Most physicists interpret this not as evidence that black holes do not exist. The observational evidence for their existence at this point is beyond serious dispute, but as evidence that general relativity, brilliant and thoroughly validated as it is across an enormous range of conditions, is not the final, complete theory of gravity. Somewhere between the well-tested regime where general relativity works extraordinarily well and the singularity where it produces nonsense, there must be a more complete theory waiting to be discovered. One that would presumably show that what looks like an infinite density from the perspective of relativity alone is actually something finite, exotic, and currently unimaginable once properly combined with quantum mechanics. This unification, a working theory of quantum gravity capable of correctly describing what actually happens at a black hole singularity, is one of the central unsolved problems in all of theoretical physics. Various candidate approaches exist: string theory, loop quantum gravity, and others, each proposing different pictures of what might replace the singularity once quantum effects are properly accounted for. None has been experimentally confirmed. The energies and scales involved are so far beyond anything achievable in a laboratory on Earth that direct experimental testing remains, for now, essentially out of reach, which means the honest answer to the question at the center of tonight's episode, what happens inside a black hole at the very center, where all that mass ultimately ends up, is that we do not know, not in the sense of a gap that better instruments would soon fill. In the deeper sense that our best theory, applied honestly to its own predictions, tells us that it does not know either. There is something worth sitting with in that admission. Not every mystery in science is a temporary gap awaiting the next generation of telescopes. Some mysteries sit at the exact boundary between our two deepest theories of physics, in territory where both theories are correct within their own domains, and yet cannot be reconciled with each other. The center of a black hole is exactly that kind of place. It is not merely unexplored, it is the specific location in the universe where our understanding of reality runs out. And yet, and this is the thought I find myself returning to again and again, thinking about this particular mystery, the boundary itself has become extraordinarily well understood. We have photographed the edge of the unknowable. We have measured the mass, the spin, the jets, the radiation of dozens of these objects with remarkable precision. We have watched stars vanish into them, watched dormant giants reawaken after 100 million years of silence, watched light itself bend around their shadows in exactly the pattern Einstein's century-old mathematics predicted. We have mapped with extraordinary precision the exact shoreline of a country we cannot enter and whose interior no one has ever seen. That is not nothing. It may in fact be one of the most remarkable achievements in the history of science, the careful, patient mapping of a boundary beyond which our current understanding of reality simply ends. Carl Schwarzschild found that boundary in a mathematical equation written between artillery calculations in the final months of his life. A century later, an array of telescopes spanning the entire planet turned that mathematics into an image. Somewhere in Cygnus, that boundary is still there, 20,000 light-years away, entirely indifferent to whether anyone is watching, holding a captured star in a slow, silent orbit around a place where physics, as far as we currently know how to describe it, simply stops. We have not seen what lies past it. We may never see what lies past it, but we know now, with a certainty that would have startled even Einstein, exactly where it begins.